Let's consider some more examples. What if our example is this series here? First thing you might try is the integral test. And that theoretically would work, but it'd be hard. Because to do the corresponding improper integral of 1 over x cubed plus 1, you'd have to integrate 1 over x cubed plus 1. You have to factor x cubed plus 1 and use partial fractions, and one of the factors would be an irreducible quadratic, and you don't want to go there if you don't have to. It's better to realize this series is very similar. This is similar to the series where it's 1 over n cubed. And that's a p series that we know converges because the p is 3 and 3 is bigger than 1. But this, saying it's similar to that, is not technically a proof of convergence. What's the proof of convergence? We think it probably converges because it's similar to this one. But how do we know for sure with a rigorous argument that it converges? You technically need the comparison test for series. We did talk about a month ago, I think. Yeah, it was over a month ago. It was in late February. The comparison test for integrals. I even put a problem on it in exam 1. The comparison test for series is pretty similar, except with series instead of integrals. We need to be formal about it because being formal illustrates the logic of how you use theorems. And we do want to emphasize that is an important thing to be able to do. We just should define an to be the terms of our series. Notice no summation sign there. And Bn is going to be the terms of the other series that we are comparing it to. Now, just because it's similar to this series doesn't mean that using this an and this, or using this Bn is going to be the good thing to do. I have to know that the ans are always less than the Bns. They are. That's good. Makes this one easier because if I add 1 to the bottom of the fraction, that makes the whole fraction smaller. This fraction is smaller than that. It's also important to say these are non-negative things. Then 0 is less than or equal to an is less than or equal to Bn for all n greater than or equal to 1. These are important things to state when you use the comparison test for series, just like we stated similar things for integrals. We know that the sum of the Bn's, being a p series with p equal to 3, which is bigger than 1, converges. Therefore, the series we're interested in, the sum of the ans, also converges by the comparison test. You should say what you are using, the comparison test in this case. We're done. Praise the Lord for that. It's a very, very common mistake, especially in the rush of an exam, for people to not bother putting summation signs in here and here. If you make that mistake, you have made technically a very, 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 very bad mistake. It's not something that's a small mistake to forget the summation signs. Now, it's understandable maybe in the stress of an exam to forget them. So I don't give you 0 on the problem, but I do take off some points. Because if you forget the summation signs here, you're completely missing the point. Again, these ans and the Bn's are terms of the series. They are the sequence numbers that are being added in the series. But the proof is about the series, the infinite sums, and their convergence or divergence, not about the terms. The terms do go to 0, both of these, So the divergence test does not apply. There's a possibility these series converge, but you actually have to use your knowledge for this one and this proof for this one to know you have convergence. This one converges because of the integral test. This one now we're proving converges because of this comparison test. You must put the series, the summations in these spots for full credit. And again, if you forget the summations, you are truly missing the point of what we're doing here.